Here we have another MapCounts national problem. So this was like 2024, team number 10. So the figure shows 25 identical white unit cubes and 2 identical gray unit cubes arranged and assembled into a large 3 by 3 by 3 cube. And how many ways are there to assemble 27 unit cubes into 3 by 3 by 3 cubes such that no faces, edges, or vertices of 2 gray cubes touch? So we are given 2 figures A and B. So this is one of the valid arrangement, and this is another one. But it says right here, however, the gray cubes are indistinguishable. Okay, and from one to another as the whites as well. So simply swapping 2 grays with the other gray in figure like P doesn't give us different like arrangement. It's going to be considered the same. And also, like we are told, the gray cubes. Okay, I mean the figure B can be rotated to get the figure A. So which is why these will be considered the same. Okay, so it's kind of a bit kind of harder to kind of start with. But let's see if we can kind of organize our counting. So what I will try, like maybe we can kind of go with the each common like position. Like what I mean by that, like for example, if you take the one of the corners, which I can call maybe as my corners. So like if I say like corner, so like if I take this corner, for example, like this has the same kind of position as this corner or this corner. What I mean by that same position, like they have the same like number of the selection because they're kind of like symmetric in one setting. So which is why when you know one of the corners behavior, then you can actually just multiply by the number of corners that we have. So which I'll go with that. And like for example, if I take this like cube, so then this cube does touch any of the cubes in this region that is 2 by 2 by 2, right? Which is going to be like 4 cubes actually, 2 by 2 by 2. Yeah, we have 1, 2, 3, 4, and then 4 in the back. So that's 8 of these. So but of those 8 cubes, this is the one itself. So which means we actually have 7 other cubes that we do have connection with this corner. So what I'm trying to right now count is the bad cases where we don't want to actually have, because that's kind of easier to count. So which is why I'll say this corner is one of the 8 corners. Like this is one of these corners, right? These are in the same position, and each one of these 8 corners has 7 other cubes that will be just next to somehow. So which is why there will be 56 and I will say pairs is not going to be what we are looking for. Okay, so that's something. And another thing we can have is maybe think about the corner in the edge. Like I'm going to call that edge, maybe like middle, so like, or center, whatever you call. So let's say as edge center. So for example, like this guy or this guy or this guy, like there is 2 in here, but there is 2 in this other sides as well. That means 4 on the bottom. And the same idea with these, we have 4 at the top. And we do have like some in the middle as well. Like this one is also edge middle. So the center of the edge, this is also center of edge. So like we have 4 more in the middle, which basically we have 12 of these. So like we have 12 like squares that is in the middle of the edge. I don't want to take this guy yet because this has more connection than this edge that we call that edge center. So like, for example, if I take the, I don't know, like say this guy. So this guy touches everything on these 3 and these as well as these 3, and then as well as this row as well, which means if you think about this as like 2 by 2 by 3, which is basically 12, and there are 12 like cubes that this guy is touching, but one of those 12 is just itself, so which means we have 11 other cubes that will be touching. So I kind of say like 2 by 2 by 3, because if I had, let's say, 4 by 4 by 4 cube, then counting will be a bit messy, so which is why it's going to be easier to go with that approach if you have 4 by 4, 5 by 4, or some other arrangement of this like question. Anyway, so that's the second case that I have kind of bad, like bad pairs. And what else do we have? Like we have the center of the faces, right? So these are the center of the faces. So I'll call the face center. Okay, so if I go with face center, so like we have 6 faces, so each face has one of these, and then they're the same. But let's think about maybe this face or that face. It doesn't matter which one you choose. You can kind of use anyway. But this face touches everything on the top row, right? Top layer, I would say. So which is 9 of that. But that's also touches anything in the bottom row as well, even this one, because the corner right here, the touches this bottom like edge of this middle as well. So which means we do have like a 2 by 3 by 3, which is just 18. But one of them is itself, so which is going to be 17 more. So we should have 17 other cubes that we actually have. So which is like 102. And maybe I should multiply this as well. So the last case that I have is the one that right in the middle that we didn't count. So maybe that's going to be cube center. Okay, so that's just one of these cubes. But the thing is, the middle cube has intersection with any other cubes, which we have 26 others. So which is why we have 26 like bad pairs with the middle guy. So like when you look at all these cases separately, they are actually exclusive, which basically means they have no common like pairs that we counted twice, other than the pair that we actually double every time. So what I mean by that, like when I say like this pair, right? So when I take this pair And then this is one of those pairs, like, so this guy and this guy will be one pair. But when I take the face cubes, like face pairs, this guy and this guy is one of those pairs as well, which means every one of these counting is actually doubling what we are going to need to count. So which is why we're going to divide this by 2. But the thing is, these are the bad ones. Like, but what is the like the total? Because if you are using the complementary, we need actually the total number as well. So which is like we have 27, and then I just need 2 cubes, and then 27 choose 2 ways. We actually have a number of selections. So which is like 27 times 13. So 27, 26 over 2, which is this number. So I think it's going to be, we can easily multiply it. And like, if you multiply 30 by 13, that will be 390. And then you need to subtract like 13, which is 39. So which is going to be 351. Okay, so this is the total cases. So now I'll just say 351 minus, we need to add all these guys. So 56, 132, 102, 26. Again, every pair is counted twice, which is why we do divide this by 2 to fix that we're counting. So if you like add these, that will be 316 and divide by 2 and subtract from this guy. So we'll get 193. So this was like interesting question. I kind of like this problem in a way that because it's not really require a lot of work, especially for being like number 10. But at the same time, this question kind of reminds me something called Chebyshev distance approach. I'll say it's not really needed for this problem, but it might be good to review such a thing, especially for people who are aiming for national stuff. So and then if you kind of have like 4 by 4 by 4 cube, so that might be a slightly better approach than this one. But anyway, so I'm gonna leave that for you to extend the knowledge. Anyway, I'll see you in the next video.